Hey, what's up you lot? Parth here, back at you with part 2 of what I think is one of the coolest theorems in quantum mechanics, Ehrenfests Theorem. In part 1, we discussed what quantum operators and commutators are, and I highly recommend you check out that video first, check it out up here, before you watch this one. In this video, we will once again be using high school level mathematics, nothing more complicated, to learn one more idea that's important, highly important, in quantum mechanics, and then we'll be using everything we've learned so far in part 1 and in this video to understand what Ehrenfests Theorem is trying to tell us. If you enjoyed this video, please do hit the thumbs up button and subscribe to my channel for more fun physics content. And by the way, I'm super thankful for this video's sponsor, Skillshare. We'll talk about them in a minute though, but for now, let's get into it. Okay, so having understood what quantum operators are, we saw that they were mathematical ways of representing how we make measurements in quantum mechanics. And having extended that to understand what quantum commutators are, which is a representation, by the way, of the order in which we make measurements in quantum mechanics, the last concept we need to learn about before being able to understand Ehrenfests theorem is expectation values. Let's start by recalling that in quantum mechanics, we work with wave functions. If we're studying a quantum system, let's say in this case just a single electron, then the wave function is directly related to its probability distribution. For example, how likely we are to find an electron at a particular point in space. But in essence, the probability distribution, and hence the wave function, just tells us how likely we are to get certain results when we make certain measurements. Now, because quantum mechanics is inherently probabilistic, that is, before we actually make any measurement on our system, we can only calculate probabilities. One quantity that we can calculate mathematically that's useful to us is known as an expectation value. An expectation value is essentially an average, a weighted average of a probability distribution. Simply put, if our probability distribution for the position of our electron looks something like this, that is, it's most likely to be found at this position, slightly likely to be found at, say, these positions, and less likely to be found at these positions, then the expectation value of the position of the electron is just the average position of the electron. And now this is a fairly simplified example. The probability distribution is symmetric about the central position, so we just happen to find that the expectation value, the average position of the electron, is right in the middle. But it's worth noting that the expectation value of our electron's position is not necessarily the position at which we're most likely to find it. The expectation value is not the modal value, it's actually the mean value. An example that should make this clearer is if we assume that our probability distribution now looks like this. In other words, we're highly likely to find the electron at either this position or this position, and extremely unlikely to find it here, here, or here. In fact, for the last 3 positions we discussed, as we can see from the graph, there's a 0% chance of finding the electron. So, what is the expectation value of the electron's position for this probability distribution? Well, luckily, this probability distribution is symmetric once again, and so its expectation value, its mean value, is right down the middle. But, as we've already seen, there's actually no chance that we'll find our electron at this position for this particular distribution. And so, as we can see, the expectation value is not necessarily the position at which we're most likely to find the electron, it's just a weighted average. Now, a quick note about expectation values. Whenever we find the expectation values of a particular measurement operator, say the position operator, which is what we've been looking at until now, we write it like this. The pointed brackets tell us that we're finding the expectation value, and in this case we're finding the expectation value of the position of the electron. However, this notation is actually a shortened notation. In quantum mechanics, technically we should write this instead. We're technically applying the position operator to the ket psi, which is the wave function of our system, and this wave function of course directly correlates to our probability distribution, which is how we encode for that probability distribution when finding the average value or the expectation value. First of all, if this is confusing for you, I'll leave some resources in the description below about averages and expectation values. And secondly, you might be asking the question, why is this even a useful quantity to know? Because as we've seen already, this doesn't necessarily mean the position at which we're most likely to find the electron. In fact, in some cases we've seen that the electron has 0% chance of being found there. So why do we even care about the expectation value? Well, because expectation values actually give us some real insight and intuition into the world of quantum mechanics. For example, expectation values can be used as a link between quantum physics and classical physics. Classical physics comes a lot more intuitively to us, it's much easier to visualize, whereas quantum mechanics is all weird and probabilistic and difficult to understand. And sometimes, certain expectation values behave like classical quantities. Ehrenfests theorem is a really good example of this, and we'll talk about that in a second. But before we do, I want to take a moment to thank this video's sponsor, Skillshare. Skillshare is an online learning community where you can find a large number of inspiring classes, focusing on topics such as productivity and lifestyle, to building a career or business, to learning creative skills in areas like music, film, and web development. As many of you will know, I'm a huge advocate of having multiple passions in life, and I've taken a few classes on Skillshare that have been genuinely eye-opening to me. For example, I took a class called Simple Productivity: How to Accomplish More with Less by Greg McEwen. And he provided some simple and easily actionable ways in which we can boost productivity. Skillshare has a large number of classes to choose from, and it's all about learning, so there are no adverts. Most classes are less than an hour long, which means it's not a major commitment to sit down and learn something new. There's also a simple but effective level system to help you hone in on classes that will be most suitable to you, and Skillshare costs less than $10 a month when you get an annual subscription. However, the first 1,000 people to click the Skillshare link in the description below will get 2 months for free. Big thanks again to Skillshare for sponsoring this video. Okay, so we've talked about quantum operators, commutators, and expectation values. So, with our understanding of these three ideas, let's check out Ehrenfest's theorem. Now, you might spot a couple of things that look a little bit familiar. For example, we can see some operators in Ehrenfest's theorem. You can tell they're operators because they're wearing little hats. And we've got some square brackets. That tells us we've got a commutator. And we can also see pointed brackets, which tells us that we've got some expectation values. In fact, a fair few expectation values in here. It's also worth me pointing out here that we've got the Hamiltonian operator in the Ehrenfest theorem. This, as you'll recall, accounts for the kinetic energy and the potential energy of our system. It's a very important operator in quantum mechanics. It comes up all over the place, even in the Schrödinger equation. And aside from the Hamiltonian operator, we've also got these A's all over the place. Now, A is just a generic placeholder for any other operator that we want to substitute into Ehrenfest's theorem. The idea is that we can take another operator, say the position operator, and substitute it into Ehrenfest's theorem wherever we see the A operator. Or we could do this with the momentum operator, or even the Hamiltonian. So A by itself doesn't mean anything, it's just a generic placeholder. Now, one more thing we need to take a brief look at is this, d by dt. Many of you will have come across differentiation, or calculus in general, before. But basically, d by dt just tells us that we're looking at the rate of change of whatever quantity comes after d by dt with respect to time. For example, if we say that in classical physics, y is the position of our cricket ball, then dy by dt is a measure of how quickly that position changes with respect to time. Or in simpler words, how much that ball's position changes per unit time. It's actually a measure of that ball's speed. And so d by dt is just a measure of how much any quantity placed after it changes with respect to time. So, coming back to Ehrenfest's theorem, what we can see here in this particular term is that we've got the expectation value of some operator A, and we're finding the rate of change with respect to time of that expectation value. This sounds really complicated, but it'll become really intuitive when we plug in certain operator, say the position operator, into Ehrenfest's theorem. But before we do that, let's quickly come to the right-hand side of the equation, where we see some more complicated terms. One of the terms that we've got is the expectation value of the rate of change of the operator A. Firstly, the d's are curly rather than the normal way that we write d's. For our purposes, we're not going to go into what that means, but if you do want to know, look up partial derivatives. But what this term is looking at is the rate of change of an operator itself with respect to time, and then we take an expectation value of that rate of change. Now, in the case of the position or the momentum operator, which are the two main operators that we'll be talking about shortly, these operators do not change with respect to time. Remember that an operator corresponds to making a measurement in real life, and how we make a measurement of either position or momentum does not change with time. The end result of when we apply our operator to our system can change with time. What I mean by that is that we can get different results when we make measurements on our system at different times. But the process of measuring itself does not change with time, and hence the operator itself does not change with time, which means the rate of change of our operator is 0. And the expectation value of 0, or the average of 0, is 0. This other term, meanwhile, is a little bit more interesting. What we're looking at first of all is 1 over I h bar, and for the purposes of this video, I and h bar are just constants. I is the square root of -1, so it's an indicator that quantum mechanics is inherently a complex theory, and h bar is known as Planck's constant. It's a scaling factor in quantum mechanics. But again, for our purposes, these are just constants. We don't need to worry too much about them. And what we're more interested in is the rest of this term, the expectation value of the commutator between A and H. We've already seen that a commutator is a useful way of quantifying what happens when we make two separate measurements on our system, and more specifically, the order in which we make those measurements. But for now, all we're interested in is substituting A for some operator, say the position operator, and then just calculating what happens mathematically, which we won't go into, but the end result becomes really interesting. So like I said, let's start by substituting the position operator into the Ehrenfest theorem. Everywhere we see an A hat, we replace it with an X hat. As we've already said, this term is 0 because the operator itself doesn't change with time, and so its rate of change is 0. And then we do all the mathematics involved in, say, finding the commutator between X and the Hamiltonian. This bit is fairly mathematically involved, but ultimately not essential for what we're going to be talking about. Feel free to pause the video though and look through the maths. I do want to make a separate video discussing all of this in a bit more detail, so do look out for that. But as I say, for now, not important. The important thing is what we get when we've done all the mathematics. When the dust settles, what we find is that the rate of change of the expectation value of the position of our electron in this case, multiplied by the mass m of the electron, is equal to the expectation value of its momentum. If we think back to classical physics for a second, let's recall that the rate of change of the position of, say, a cricket ball with respect to time is the same thing as its velocity. And when we multiply the velocity of an object by its mass, we find its momentum. And this is where Ehrenfest's theorem links classical physics to quantum mechanics. The equations look similar, but now we're dealing with expectation values, whereas in classical physics we can deal with the actual position and actual momentum of our object. So even though quantum mechanics is weird and deals with probability distributions, if we look at expectation values, they behave a lot like we expect in classical physics. Regardless of how the probability distribution of the position of our electron changes, its average value, its expectation value, behaves in such a way that if we find its rate of change, or how it changes per unit time, and we multiply that by the mass of our electron, then we find that it's equal to the expectation value of the momentum of our electron. Going back again to the general version of Ehrenfest's theorem, we could also substitute the momentum operator instead of A. And under some very specific conditions and making some specific assumptions, we would end up with this. What we find is that the expectation value of the momentum operator behaves like Newton's second law tells us the classical version should behave. But we won't go into that too much here because it's very fiddly and very subtle. The key takeaway here is that even though quantum mechanics deals with probabilities, if we study expectation values, in many cases those expectation values behave like their classical counterparts. And we've also seen why Ehrenfest's theorem can be thought of as a link between classical physics and quantum mechanics. And with all of that being said, I'm going to end the video here. Thank you so much for watching. If there's something I haven't explained clearly enough, then do leave a comment down below and I'll try and reply. And if I've made a mistake, let me know as well, and we'll try and fix that as quickly as possible. If you enjoyed this video, please do hit the thumbs up button and subscribe to my channel for more fun physics content, and feel free to hit the bell button if you want to be notified when I upload. I'm currently working on another video which is going to be about entropy, so if you're interested then please do keep an eye out for it, and I'm going to be trying out something new with that video as well. As always, thank you so much for watching. I'll see you really soon.